Here we have the general form of the Biot-Savart law right here. And so to take the full integral over all tiny pieces of current that's going through this wire, we'll need to integrate both this side and this side of the function. And that will give you the total B field that is produced from all of these little infinitesimal pieces of current going through a wire. And we'll say current's going up, but in this case, it doesn't matter. So if I integrate over all B, it'll come out to be just this. We're going to go ahead and take mu naught, 4 pi out, I out, and then we'll go ahead and put an integral sign over ds, cross product over r, and then r cubed. And this ds is an infinitesimal piece of this current here from 0, goes negative infinity to positive infinity. So this is an infinite wire. We're going to go ahead and put negative infinity to positive infinity as the limits of the integration. Now, let's go ahead and analyze what ds cross r is. Well, any cross product is really just a scalar version of both variables that are within the cross product times sine theta. And where theta is 90 degrees, that's where both of them are perpendicular to one another. So let's go ahead and just take the definition of a cross product in terms of sine theta. That will make it to r over r cubed times ds times sine theta. And I think it'll be more appropriate to put sine theta before the ds, just so it looks a little bit better. Well, this is a problem because we have ds, we have theta, and we have r. All of them are variables. And so we need to get this whole integrand in terms of ds or any one variable, and we need to get d in terms of a particular variable as well. And that needs to match the integrand. So let's go ahead and simplify this a little bit more. And then we'll go ahead and analyze a few things to try to get this going. So this reduces to 1 over r squared sine theta ds. We have 3 variables. We have s, theta, and r. First thing, I'm going to go ahead and look at this. And what this looks like to me is a triangle. So what I'm going to do is I'm going to say let s equal to r over tan theta. And I'll show you why that works. Using the ideas of SOHCAHTOA, we can see that tan of this theta here is equal to the opposite leg over the adjacent leg. So tan theta is r divided by s. So if I want to get s isolated, I take s from one side of the denominator to the numerator of the other side, and that just becomes s tan theta equals r, and then I take tan theta to the denominator of the right side. So s then becomes r divided by tan theta. So if that's the case, then we'll let ds equal to r. And this is actually tan negative first theta. The derivative of that is just going to be tan theta to the negative second power multiplied by the derivative of tan theta via chain rule. And that's going to be secant squared theta and then d theta afterwards. Okay. So this is going to be ds. And we're seeing something interesting here. We see that tan theta is on the bottom squared, secant squared theta is on top. And this would come out to be, just make it look a little bit more palatable here. It'll come out to be this. These can be broken up into sines and cosines. So let's go ahead and do that. A secant is a 1 over cosine. So, and a tan is a sine over a cosine. So let's go ahead and do that. Secant squared theta is 1 over cosine squared theta. Tangent on the bottom squared theta is sine squared theta over cosine squared theta. But since it's on the bottom, cosine squared theta goes up on top. Sine squared theta goes down on bottom. And then we have d theta at the end. Cool enough. The cosine squared thetas cancel out, leaving sine squared theta here. Let's go ahead and pull it up here, complete this calculation. We then have r over sine squared theta d theta. Sine of theta, so not the squared, but just the sine of theta is equal to opposite over hypotenuse. So let's go ahead and add that in. Since sine of theta is r over little r, then we have ds equaling to r divided by r over little r squared, d theta. And that's going to come out to be r squared over big R squared. These cancel out, sorry, d theta. And this comes out to be r squared over big R d theta. Okay, well, that looks a little bit better. Let's go ahead and plug it into our original calculation. So now we have b equaling to mu naught over 4 pi I, 1 over r squared sine theta. And now ds is going to just be r squared over r d theta. Well, luckily for us, now I kind of knew this already, but you wouldn't be satisfied with having two variables at the end unless you knew that if you plugged it in with the rest of the integrand, one of the variables would cancel out. And so since I already knew that, I was happy with doing that. Okay, so now we get to reduce our integrand a little bit more now. This r is a constant, so we'll take that out. So b equals mu naught over 4 pi r times I sine theta d theta. Now we got to reanalyze the limits of the integration since we've changed from ds to d theta. It's no longer from negative infinity to positive infinity. It is now going to be from, well, let's see, if we're way down here and the infinite bottom part of the current line, theta is going to essentially be 0. And if we're way up here at the very top, all the way to infinity, this theta will then go up to about 180, right? So that would be pi in radian terms. So now we have our new limits of our integration, and now we could finally solve it for b. The integral of, I'm going to go ahead and just put I up here finally. The integral of sine theta is negative cosine theta. And now with the limits of integration, we can go ahead and analyze what this comes out to be. I'm going to add a little bit of, put a little side quest here, just so we can analyze this without rewriting all of this other stuff, the coefficients. So negative cosine of pi minus negative cosine of 0 will be what we want here. We'll put the negative in front, and then we'll just analyze cosine of pi minus cosine of 0 in this parentheses. Cosine of pi is negative 1 if you look at the unit circle. Cosine of 0 is going to be positive 1. So negative 1 minus a positive 1. Comes a little confusing with all these negatives and positives. So negative 1 minus 1 is a negative 2, but then there's a negative in front, so it becomes a positive 2. So now this whole thing is just 2. Let's go ahead and put it here. This becomes mu naught I. Now, since 2 is on top, it cancels out half of this 4 on the bottom. So the bottom becomes 2 pi r, which is actually what we wanted to prove. Mu naught I over 2 pi r is the B field for this particular setup.